In this video, we will derive the strain displacement matrix for a CST element. We know that CST stands for constant strain triangle. This element is a triangular element with 3 nodes. When we derive the equations for strain, we will see that the strain is a constant anywhere in the triangle. We also know that the nodal displacement values are u1 at node 1 and v1, u2, v2 at node 2 and u3, v3 at node 3. U is the x component and v is the y component of the displacement. The displacement at any point within the element can be represented with u and v components, and we know that u is equal to n1 u1 plus n2 u2 plus n3 u3. u1, u2 and u3 are the nodal values of displacements, and n1, n2 and n3 are shape functions. Similarly, we can write an expression for v, the vertical component of the displacement. And the shape functions are n1 is equal to psi, n2 is equal to eta, and n3 is equal to 1 minus psi minus eta when we use the natural coordinate system. We use the natural coordinate system to simplify our analysis. I'll give you a quick review about the natural coordinate system before we move into the derivation of strain displacement matrix. If you want to mark a point P in the global coordinate system, we will just specify the x coordinate as well as the y coordinate. As an example, if our x value is 4 and y value is 3, we will mark the x and y as 4, 3. And we also know that the x and y values are 0 at the origin. Here is the origin. In natural coordinate system, we mark the same point P using psi and eta. I'll quickly mark the values of psi and eta at this point P to illustrate how natural coordinates work. The value of psi is 0 at the node 2 and node 3, or along the line joining 2 and 3, if anywhere the value of psi is equal to 0. Parallel to line 2, 3, the value of psi increases from 0. Say it is 0.2, 0.3, 0.4 and so on. Finally, the value reaches 1 at the node 1. So this is how the value of psi increases from this line towards the node 1. So approximately let me mark a value of 0.254 psi. The way to calculate it is you take the area of the triangle as A and you mark another triangle joining the lines 2P, P3 and 2,3. That triangle you take the area as A1 and the value of psi, you know, that is equal to A1 by A. Now the value eta. Eta value is equal to 0 at node 1 and node 3, or along the line joining 1 and 3, everywhere the eta value is equal to 0. Now the value of eta is going to increase parallel to the line 1, 3, and it increases to a value of 1 at node 2. So here it may be 0.1 along this line, the value of eta increases, and here it might be 0.8, and finally at node 2 eta is equal to 1. At the point P, it can be from here increases from 0.1 point to say 0.3, the value of eta. And if you want to calculate the value of eta, what you can do is you can draw the triangle joining 1 P3 and calculate this area as A2, and we know that if the area of the triangle is A, eta is equal to A2 by A. We can also write a relationship between xy and eta and psi, provided you know the values of x1, y1, x2, y2 and x3, y3, which are the xy coordinates at node 1, 2 and 3. X is equal to x1 minus x3 into psi plus x2 minus x3 into eta plus x3, and y is equal to y1 minus y3 into psi plus y2 minus y3 into eta plus y3. We have also seen that the expression for u is equal to u1 minus u3 into psi plus u2 minus u3 into eta plus u3, and v is equal to v1 minus v3 into psi plus v2 minus v3 into eta plus v3. So we can use these expressions to calculate the value of u and v at any inside point. What we have to substitute is, at the point we have to substitute the value of psi and eta, and also the nodal displacement values u1, u2 and u3, u1, u2 and u3. And if we want to calculate v, we have to substitute the value of v1, v2 and v3. Also, for both uv and xy, we use a similar kind of expression. You can see both these cases. Or we say that we use the same shape functions to write expressions for both uv and xy. This is known as isoparametric representation. That is, same shape functions to interpolate uv and xy. With this knowledge, we can now go into the derivation of strain displacement matrix. For a 2D problem, we know that the strain components are epsilon x, epsilon y and gamma xy for both plane stress and plane strain problems. And the displacement components are u is equal to u and v. The strain displacement matrix relates the strains epsilon with the displacements u. We also know that epsilon x is equal to dou u by dou x, and epsilon y is equal to dou v by dou y, and gamma xy is equal to dou u by dou y plus dou v by dou x. We know that the value of u and v changes with the position inside the element, and we can write that u is a function of x and y. From these equations, we know that x depends on psi and eta value. So x is a function of psi and eta, and y is also a function of psi and eta. So u is a function of x and y, and x is a function of psi and eta. Our job is now to find the expressions for these derivatives, dou u by dou x, dou v by dou y, and this derivative. For that, we will first write the expression for dou u by dou psi. Using chain rule, we can write dou u by dou psi as dou u by dou x by dou psi plus dou u by dou y into dou y by dou psi. This is the chain rule. And the matter of fact that u is a function of x and y, and x is a function of psi and eta. The expression for dou u by dou eta can be written as dou u by dou x by dou eta plus dou u by dou y into dou y by dou eta. From these expressions, we will be able to find dou u by dou x, dou u by dou y, dou u by dou x, dou u by dou y, so that we will reach the halfway by calculating epsilon x and this term. Let us write these equations in the matrix form. The left hand side are these two terms. I have written that as a vector. This is equal to some matrix into another vector. I'll write these highlighted terms dou u by dou x and dou u by dou y in this vector. Now we can fill the remaining terms inside these matrix. The first row would be from the first equation. So the first element is dou x by dou psi. The second element is dou y by dou xi. And the second row will come from the second equation. So dou x by dou eta here and dou y by dou eta at the last element. I have changed the color for you to quickly identify where these elements are coming from in the matrix. I will write this matrix as the J matrix. This is the Jacobian of transformation. What we want to find is dou u by dou x and dou u by dou y. So what we can do is just invert the matrix J to find dou u by dou x and dou u by dou y. So dou u by dou x and dou u by dou y is equal to J inverse of dou u by dou psi and dou u by dou eta, where J is this matrix. Now we need to find J inverse. The inverse can be calculated as adjoint J by determinant J. Before finding the inverse, let us first determine these derivatives. We have the expression for x and y in terms of psi and eta. I would like to also introduce a compact notation to represent x1 minus x3, x2 minus x3, and so on. Let me represent x1 minus x3 as x13 and x2 minus x3 as x23. Also y1 minus y3 and y2 minus y3 as y13 and y23 respectively. So the equations for x and y can be written as x equal to, instead of x1 minus x3, x13 psi plus x23 eta plus x3. Similarly, we can also write an expression for y as y13 psi plus y23 eta plus y3. Always remember that y13 means y1 minus y3 and x23 means x2 minus x3. Let's find these derivatives now. First, dou x by dou psi. So if we differentiate x with psi, these two are constants, so you will get x13. Second, dou y by dou psi. So we differentiate y with psi partially. So what you're going to get is y13. Similarly, dou x by dou eta should be equal to x23, and dou y by dou eta should be equal to y23. Let's substitute these values in the place of the derivatives. So we get the matrix J as this. To find the adjoint of the matrix, first we have to write the minor of the matrix. To get the first element in the minor, what we do is we consider the first element in the matrix and we cross the corresponding column and the row, and what we get remaining is return. So y23 comes here. For the second element, you consider the second element here. You cross the corresponding column and the row. The remaining element is written over here. x23 comes here. And the third element here, you consider the third element here. You cut the column or the row and the column, and what remains is written over here. And the last one is x13. You do the similar procedure. Now the next step is to get the cofactor matrix. This matrix is a 2-row and 2-column matrix. The first element is actually the first row and first column. I am writing the row and column index here. The element here is the first row and the second column. So the integers are first row, second column, and this element is second row, first column. So the integers are second row, first column, and the last element is second row, second column. Let me write the indices as 2, 2. So what I have written are the indices. If you sum the integers, this element will have a even number. 1 plus 1 is 2 is an even. This is 1 plus 2, this is odd, 3 is odd. The sum here is odd and the sum here is even. Now to get the cofactor matrix from the minor of the matrix, what you do is, if you have the element even, then you give a plus sign. If the sum of the integers are odd, you give a minus sign. So here that would be plus. Here, since the sum of the integers is odd, you give a minus. Here also the sum of integers is odd, so you give a minus. And the last one, the integers, the sum is even, so you give a plus. Now this matrix is the cofactor matrix of the matrix J. Now to get the adjoint, what you have to do is take the cofactor matrix and take the transpose of that. So adjoint of the matrix is the cofactor transpose. So you take the first column and write it as a row here, and take the second column and write it as a row, second row. Now you got this part. Now you have to find the determinant J. So determinant J is equal to, you take this diagonal, x13 into y23 minus y13 into x23. If you remember, x13 is x1 minus x3, and x1 is the x coordinate of the first node of the triangular element, and x3 is the x coordinate at node 3. So if you evaluate this determinant, what you get would be the twice of the triangle's area. So I'll write this equal to 2a, where a is the area of the triangle. Now we can write the inverse of the J matrix. So 1 by determinant J is 1 by 2a, and adjoint J is y23 minus y13 minus x23 and x13. So we have found the J inverse, so we can substitute J inverse in this equation. But before doing that, let us evaluate these two derivatives also. We can differentiate the expression for u to get dou u by dou xi. Dou u by dou xi should be equal to u1 minus u3, and dou u by dou eta should be equal to u2 minus u3. Now in this expression we can substitute J inverse as well as these two derivatives from here to finally get expressions for dou u by dou x and dou u by dou y. Dou u by dou x, dou u by dou y is equal to J inverse. J inverse is 1 by 2a into y23 minus y13 minus x23 x13 into dou u by dou psi, which is u1 minus u3, and dou u by dou eta, which is u2 minus u3. We can do a similar procedure to find the other two derivatives, which are dou v by dou x and dou v by dou y, by considering this expression also, which is v is equal to v1 minus v3 into psi plus v2 minus v3 into eta plus v3. This would be equal to again 1 by 2a into y23 minus y13 minus x23 x13 into, instead of u1 minus u3, here it would be v1 minus v3, v1 minus v3, and the second term would be v2 minus v3. I'll number this as equation 1 and equation 2. I'll expand these matrices to get an expression for dou u dou x, dou u by dou y, dou v by dou x, and dou v by dou y. If we expand equation 1, that would be equal to 1 by 2a into, you have to multiply this row with this column to get the first element, and the second element this row into this column. The first element would be y23 into u1 minus u3 plus minus y13 into u2 minus u3. The second element would be minus x23 into u1 minus u3 plus x13 into u2 minus u3. If we further expand these terms, this would be y23 into u1. Then there is only one u2 term here, that would be minus y13 into u2. Then we have y23 into minus u3 and plus y13 into u3 plus y13 minus y23 into u3. The same way I can expand the second row also, and we get minus x23 into u1 plus x13 into u2 plus x23 minus x13 into u3. Also notice that I have used square brackets to represent this 2 by 2 matrix, and for a column vector I have used curly brackets. Here this is also a column vector with 2 elements, so that is why I am using a curly bracket here. Also, I would like to make a few changes. I want to remove this minus sign from here. Also, I want to expand these two brackets as well. Let us now take minus y13. We know that y minus y13 is equal to minus of y1 minus y3. So that is equal to y3 minus y1. Or this is simply, if you follow the notation, y31. So negative y13 is y31, and here there is also one more negative term, minus x23. So minus x23 should be equal to x32. Now let us take this term inside the bracket and expand and see what it is. y13 minus y23 is equal to y1 minus y3 minus y2 minus y3. So here you have got a minus y3 and minus y3 here. So what remains is y1 minus y2, or this is simply y12. Or the rule to subtract y13 and y23 is you take the first index here, that is y1, and this is y2. When you have 3 on both sides, then what you get is y12. 12 forms the first index of these two terms. Similarly, x23 minus x13, so that you can simply write with the first indices. So here it is 2 and here it is 1, so x21. So from these, let me substitute this term, this term, this term, as well as this term. We get the expression as shown here. The terms I have replaced are shown in red color. Let us write dou v by dou x and dou v by dou y. That would be equal to 1 by 2a into, what you have to only substitute is, instead of u1, u2 and u3, you have to substitute v1, v2 and v3. So y23 v1 plus y31 v2 plus y12 v3, x32 v1 plus x13 v2 plus x21 v3. Now we are in a position to write expression for epsilon x, epsilon y and gamma xy. We have the value of epsilon x dou u by dou x from this expression. So dou u by dou x is equal to 1 by 2a into this line. Epsilon y is equal to dou v by dou y. So dou v by dou y is here. So dou v by dou y is equal to 1 by 2a into x32 v1 plus x13 v2 plus x21 v3. Gamma xy is equal to dou u by dou y plus dou v by dou x. Dou u by dou y, you will get it from here. Dou u by dou y is equal to 1 by 2a into x32 u1 plus x13 u2 plus x21 u3. And dou v by dou x is equal to 1 by 2a into y23 v1 plus y31 v2 plus y12 v3. Now let us write epsilon x, epsilon y and gamma xy as a column vector, and that would be equal to 1 by 2a. Epsilon x is equal to dou u by dou x, that we will get from this first line. And the second term is epsilon y. Epsilon y is dou v by dou y. Dou v by dou y is 1 by 2a into this line. So 1 by 2a into, copy this line over here. Last we have gamma xy, that is dou u by dou y plus dou v by dou x. Dou u by dou y you get as 1 by 2a into this line, and dou v by dou x is 1 by 2a into this line. So you have to sum these two and write it over here. So when I sum this, dou u by dou y contains u1, u2, u3 terms, and dou v by dou x contains v1, v2 and v3 terms. So I'll write first as u1 and v1 terms, then u2 and v2 terms, and then u3 and v3 in that order. So x32 into u1 from here plus y23 into v1 plus x13 into u2 from here plus y31 into v2, that is from here, plus x21 u3 from here, plus y12 into v3 from here. We have one more step remaining, which is I'll split this vector into a product of a matrix and a column vector, and that column vector would be nodal displacement vector, which contains u1, v1, u2, v2 and u3, v3. We have to fill the elements of the matrix. The first row is from this equation. So the coefficient of u1 is y23. So y23, coefficient of v1 is, there is no v1 here, therefore it is 0. So I'll write 0. Then the coefficient of u2 is y31, and the coefficient of v2, since there is no v2, the coefficient is 0. Then we have the coefficient of u3 is y12, and finally there is no v3 in the equation, so the coefficient is 0. Same way, the second row comes from the second equation. So here you have 0, x32, then 0, x13, and 0 and x21. There are no u terms in the second equation, so the coefficients corresponding the u terms here should be zeros. And these three terms come from here. The last row is from this last equation, and for all these u1, v1, u2, v2 and u3, v3, there is a coefficient. You have to simply write it down. The u1 coefficient is x32. Then you have y23, x13, and y31, x21 and y12. y31, x21 and y12. This is the strain, and this matrix is the strain displacement matrix B, and this is the nodal displacement vector U. You can also write this expression in a compact notation as epsilon is equal to B into U, where epsilon is this vector, U is this vector, and B is this matrix. Finally, we have the strain displacement matrix B. To easily write this, you first write 1, okay, and then you start with the y here. So after 1 you have the indices as 2 and 3, or subscripts as 2 and 3. Then alternatively you write y, and in between you have 0. So this 2 changes to 3 cyclically, 3 changes to 1. So from here 3 changes to 1 and 1 changes to 2. So you can easily write the first line. When you write the second line, all these terms are x, but you go diagonally here. So the first 1, 3 and 5 elements are 0. So here it is 2, 3. So interchange this 3, 2, 3, 1, 1, 3 and 1, 2, 2, 1. And the last line, this y23 comes from here and x32 from here, y31 and x13, y12 and x21. Also remember that these terms are notations. Say for example, x32 means that is x3 minus x2, and x3 and x2 are the coordinates of your triangular element. So x3 you can get from the third node, the coordinate x coordinate of the third node, and x1 is the x coordinate of the first node, x2 is the x coordinate of the second node. So you can evaluate this B matrix if you know the x, y coordinates of the nodes of the triangle and also the area of the triangle. This area of the triangle you can calculate from the determinant. If we go back to the equation for strain, we see that what is on the right hand side is this is the area, that is the area for the triangle. All these terms inside this matrix are the nodal values for x and y coordinates, and the right side, this nodal displacement vector, the values are the displacement values at node 1, 2 and 3. Therefore, we will have a constant value for strain anywhere within the element. That is why this element is known as a constant strain triangle. We will stop here, and next we will see how to calculate the strain displacement matrix with the help of some example problems.